1 red and 3 blue paper clips in one drawer, and 1 gold and 2 silver in another drawer. And then we're going to use this area diagram to represent us drawing 1 colored paper clip, 1 like metallic. Okay. So I'm going to put the colored across here. Colored paper clips, and then these are going to be my metallic. And so this is this blue. This is red. All right, so if I were to go into that 1 drawer, what's the probability that we would get a blue paper clip? Well, how many blues are there? 3 out of how many paper clips in the first drawer? Just in the 1 drawer. Just in this drawer. 4. Okay, so we would have 3 out of 4. So 3/4 would be blue. And that means 1/4 would be red. There's 2 separate drawers. Okay, this is drawer 1. Drawer 2 has these. Okay. Silver. All right, now if we go to the second drawer, what's the probability that we would? Now, if we wanted to find the probability that we would choose a blue paper clip and a silver paper clip, and tells us to multiply. And if you look at this box in the upper left, least times 6. Right? Here? There's 1 red and 2 blue, so there's 4 altogether in the first drawer. Okay. Yeah? What? Oh, yeah, today's math. Thank you. I think I did that on geometry all day. Thank you. Yeah. We were going back in time, weren't we? Okay, so let me go back to this. So we want to draw a blue paper clip and a silver paper clip. The probability would be the least times the width. So we would do 3/4 times 2/3. You know how to multiply fractions? Almost. 6 times 12. So that would be 1/2. There's 1/2 probability that we would get a silver and a blue. Okay, we're going to fill in the rest of the boxes. What if we want to do the probability for silver and red? Okay. Multiply straight across. We'll do 2 12 or and then we can do that for gold, and we can do that for gold and blue. So 1/3, 3/4. One-third, get a gold and a red. Now, what do you think would happen if we added up all those special probabilities? So what is the probability of getting all of them out if you take them? 100% or 12 12s, right? 6 12s plus 2 12s is 8. Plus 3 more, that's 11. Plus 1 more, 12 12. So 100% of the time we get all of them. You've got all the probabilities accounted for. Right? But you got each individual as well. Get each individual probability. So multiplying, this is why multiplication has to happen if you want to do two separate events. Okay? What's the probability that Maria and then the next person to reach into the cooler will both randomly select a soft drink? Okay? Do a visual and then we're going to do the next part, okay? So, for the very first event, when Maria goes to get a soft drink, what are the two outcomes that she can get? A regular? Okay. What's the probability that she's going to get a regular drink? Very good. 8 out of 13. What's the probability that she's going to get a diet? Notice that our 2 branch adds up to be 100%. This is like drawing randomly. While you close your eyes and you just fill and you pick up a drink. Okay, so then she realizes she's not really thirsty. She puts it back, and then somebody else is going to come in and get a soft drink. So the 2 outcomes, of course, let's get a regular or a diet. What's the probability that the second person gets a regular? Well, she put it back. So how many regular cans are in the cooler? Same amount, right? So she put the can back. She drew one out. We don't know what she got, right? But she put it back in the cooler. Because if she got a regular the first time, then the second person can get a regular or diet. If she got a diet the first time, the second person could get regular or a diet. Yes, this is first person, this is second person. Well, we don't know. Alright, so if we were to do probability of regular and another regular, and tells us to multiply, so 813 times 813. And if you look at your tree diagram, regular is 813 times 813. So it's sort of a vision for what we're doing here. And of course we need to multiply this out. So 64 over 160. And then does it reduce is the question. Yes. These are independent events. When Maria draws the coat back, it has no effect on what the second person does. Right? Yeah, it looks like it does look like a ravel. Okay, like a horseshoe. That means is. Uh-huh. So we just multiply the two probabilities of our together. And okay, now remember, this time she's not. She's gonna drink one. Okay? we're going to, because we're trying to find the probability, we got a regular soft drink, okay? We're going to, because that's what it's doing. Kind of. This is 7 out of 12. Because if she's got a regular soft drink in her hand, she's only 7 regular soft drinks in the cooler. And if she's got one soft drink, there's only 12 soft drinks in the cooler. 5 out of 12, good. Still 5 diets in there, but there's only 12 people. Okay, now, if we assume that she got the diet, what's the probability of getting a regular? 8 out of 12. And if we assume now that Maria got the diet, what's the probability of getting the diet the second time? 4 out of 12. You see that? Okay. So if we look at our tree now, we want down the tree diagram. 8, 18 times 7, 12. This is just over 13 times. 160. 14 out of 39. Okay. Even though this is still a multiplication, it's a dependent event because what Maria pulls out of the cooler affects what the second person can choose, right? These numbers went down from 13 to 12. So it's dependent. So we do the probability of A multiplied by the probability of B if A happens. And again, that notation for and would look like that. You have to make a decision whether it's independent or dependent. I'm going to hand out a quick Aggie clip for you, and then I have one also that I need to pass back from last week, from Friday.